Hi, this video is about the calculation of Fourier series coefficients. So let us first remember what we mean by a Fourier series representation of a periodic function or periodic signal. X of t is an arbitrary periodic signal with fundamental period capital T0. Okay, remember a signal is periodic if x of t is equal to x of t plus capital T for all t, and t is a period. And among these periods, there may be several periods for a periodic signal. The smallest period is called the fundamental period. Now, the Fourier series representation of this signal x of t is x of t equal to a series expression k running from minus infinity to plus infinity, ak e to j k omega 0 t, where omega 0 is related to the fundamental period of the periodic signal by means of this expression. Omega 0 is equal to 2 pi over capital T0. Now also remember that the complex exponential signals, the infinite set of these complex exponential signals is called a harmonically related set of complex exponential signals because the frequencies are integer multiples of omega 0. Okay, the question is, how do we calculate the coefficients ak? Okay. Now, in order to reply that question, we have to remember certain facts about vectors in general, because the mathematical setting for the Fourier series representation is, as a mathematical structure, the vector space. And therefore, we are going to employ certain results valid for vector spaces. Now, okay, first of all, let us remember what we mean by the vector space Rn. Rn is the space of ordered n-tuples of real numbers. So if V is in Rn, V can be written in the following form. It's a vector with n entries, alpha 1, alpha 2, up to alpha n. Okay, and alpha i's are members of the real number set. for I running from 1 to n. Now, also we know that we can define similarly the space of ordered antiples of complex numbers as the vector space Cn. So this is the space of ordered antiples of complex numbers. Okay. Well, the idea is just the same, except that the vector now in Cn can be represented similarly by a vector with components or entries alpha 1, alpha 2 up to alpha n, and each alpha I is a member of C, the complex number set, for I running from 1 to n. Now, in this space, we can define an inner product of two vectors. For instance, V1, V2 are members of Cn. So V1 is, for instance, alpha 1, alpha 2, alpha n, and V2 is beta 1, beta 2, beta n. The inner product of V1 and V2 is equal to, now there are several possibilities to define an inner product, but I'm going to prefer the following expression for the inner product in this space. I running from 1 to n, we have the summation of alpha I, beta I conjugate. So, in the definition of the inner product, we have such an expression. Now, as you see, there is a certain similarity in terms of expressions between Cn and Rn, but in Rn we have vectors with real entries, and therefore in the inner product we are going to just multiply the entries and add them. However, for Cn, in the definition of the inner product, we have conjugation in the expression. We take the conjugates of the entries of the second vector, V2. The reason for this is the following. Remember that the inner product of a vector with itself, that means if V1 and V2 are equal to each other, suppose that we have V1 inner product with V1. In that case, okay, let us write it down. The inner product of V1 with itself will be equal to I from 1 to n, alpha I conjugate. But alpha I conjugate will be equal to alpha I modulus squared, which means that the inner product of a vector with itself in Cn is real valued. Okay? So this is real valued. But in general, for two different vectors, the inner product is complex valued. When we have the inner product of a vector with itself, the inner product must be real valued, because the meaning of the inner product is, in fact, it tells us, it is a measure of how much one of the vectors is contained in the other one. Okay? So in the case that when we have the inner product of a vector with itself, the expression is maximized and we have a real valued quantity. Later, in the context of inner product spaces, we will see that this expression will be nothing but norm of the vector squared. Okay. Now, in Cn, we are able to define such an inner product. Now, how do we make use of this inner product in the representation of vectors in Cn? Let us look at this problem. For the representation of a vector in Cn, first of all, we have to introduce another concept which is related to the vectors, the inner product operation. Two vectors, v1 and v2, of course I'm talking about Cn at the moment, are orthogonal if the inner product of v1 with v2 is equal to 0. Okay. Now suppose that we are able to find a set in Cn which is an orthogonal set. That means the elements are pairwise orthogonal, and we are able to find n such vectors. So let us denote them by v1 bar, v2 bar, up to vn bar. And we claim that this is an orthogonal set of vectors in Cn. Now here we omit certain details. For example, it is very easy to show that this orthogonal set is also linearly independent, and therefore it's a basis set for Cn. Okay, let us not go into the details of such concepts at the moment, because we are going to use these concepts in the evaluation of the Fourier series coefficients. That is our main aim. So in this orthogonal set of vectors, vi bar, vj bar, the inner product, is equal to 0 for I different from j, and I and j running from 1 to n. Now, any vector v in Cn can be represented as V equal to I from 1 to n AI Vi bar. So we are able to represent a vector in Cn in terms of a linear combination of these vectors v1 bar, v2 bar up to vn bar, but which also form an orthogonal set. Now, in this case, how can we calculate the coefficients in this representation? These coefficients, AIs, can be easily evaluated as follows. For example, I want to evaluate A1. So take the inner product of V with V1 bar. So the inner product of V with V1 bar is equal to, now, without proving, we will claim that we are able to interchange inner product operation and summation. I from 1 to n AI inner product of Vi bar with V1. Now we know that Vi bar will be orthogonal to V1 bar when I is different from 1. Therefore, this summation will reduce to a single term, A1 V1 bar, V1 bar. Therefore, A1 is equal to V1 bar divided by V1 bar, V1 bar, inner product of V1 bar with itself. So in general, AI is equal to the inner product of V with Vi bar divided by Vi bar inner product with itself. The inner product of Vi with itself. So if V is, the vector V is represented in terms of vectors which form an orthogonal set, it is very easy to calculate the coefficients by using orthogonality. How do we do that? If we want to calculate a particular coefficient, we just take the inner product of both sides with the vector, the corresponding vector, for example, Vi bar, and the summation will reduce to a single term because of orthogonality, and we will be able to calculate the coefficients in an easy way by using the concept of orthogonality. Now, the concept of orthogonality, the concept of inner product, can be extended to function spaces as well. Okay, for vectors, what do we do? For instance, I write the vector v1 as, okay, now a certain interpretation related to the inner product. I write v1 as alpha 1 alpha 2, etc., alpha n. Okay, in fact, we have column vectors. So let me write it as rows in this case. And v2, beta 1, beta 2, etc., up to beta n transpose. And the inner product, we calculate the inner product by means of the following expression: I from 1 to n, alpha I, beta I, conjugate, complex conjugate. Okay. Now, the definition of inner product can be extended to periodic signals as follows. Let x1 of t and x2 of t be periodic signals. With the same fundamental period. Capital T0. The inner product of x1 and x2 is defined as from T0 to T0 plus capital T0, x1 of t, x2 of t conjugate integrated with respect to t. Now, just try to notice the analogy between these two inner product expressions. For vectors in Cn, we have only n components. For example, for v1, we have alpha 1, alpha 2, up to alpha n. And for v2, beta 1, beta 2, up to beta n. We multiply alpha I by beta I conjugate and add them. Now, in the case of functions, as you see, we have infinitely many values. In fact, uncountably infinitely many values. So instead of the simple summation operation, now we have integration. We have the product x1 of t and x2 of t complex conjugate, and then we integrate over a period. So here t0 is an arbitrary value, but you can choose it. For example, if you choose it as 0, it will be an integral from 0 to t0, but you can choose any value for t0. As long as you integrate over a period, we define the inner product over a period by means of this expression. Now we have the same definition of orthogonality valid in this function space as well. So if the inner product of x1 and x2 is equal to 0, the signals x1 of t and x2 of t are orthogonal. Orthogonal signals. Okay, now we are ready to go back to the Fourier series expression. In the Fourier series expression, we have a periodic signal expressed as a superposition of the complex exponential signals. Now, for the complex exponential signals, if we are able to show that the set of harmonically related set of complex exponential signals form an orthogonal set, then by using the idea we have developed in Cn, we can calculate the coefficients rather easily. So let us now look at that problem. Okay, now in the Fourier series expression or representation of a periodic signal, we have the harmonically related set of complex exponential signals e to k omega 0 t, k running from minus infinity to plus infinity. So this is the harmonically related set of complex exponential signals. Complex exponentials. Signals. Okay. Now, can we claim that this set is also an orthogonal set? In terms of the inner product we have defined for periodic signals. So we have the following claim. The inner product of e to j k omega 0 t and e to j L omega 0 t is equal to 0 for k different from L. Okay. Now, how do we define the inner product? Remember, in the inner product, we have an integral from t0 to t0 plus capital T0. We have the first signal, e to j k omega 0 t, and then we have the complex conjugate of the second signal multiplied and integrated. Okay. Now, what is the complex conjugate of e to j L omega 0 t? Remember, e to j L omega 0 t is cosine omega 0 t plus cosine L omega 0 t plus j sine L omega 0 t. So, in the conjugation, we will have minus j representing, replacing j, and therefore this will be e to minus j L omega 0 t. Therefore, this integral will be e to j k minus L omega 0 t integrated with respect to t. Okay. Now, remember, I told you already that we are able to choose t0 arbitrarily. So let me choose it as 0, from 0 to t0. Okay, therefore, this integral will be 1 over j k minus L omega 0 e to j k minus L omega 0 t. Okay, evaluated at 0 and t0. Now remember that k and L are integers and they are not equal to each other. They are arbitrary integers. Therefore, this integral is equal to 1 over j k minus L omega 0. Now, we are going to substitute e to j k minus L omega 0 t0 minus, okay, when we substitute t equal to 0, e to j, a certain expression, times 0 means it is equal to 1. Okay. Now let us look at this term here, omega 0 t0. It is equal to 2 pi. Because remember, omega 0 is related to capital T0 as omega 0 equal to 2 pi over capital T0. Therefore, the product is equal to 2 pi. Now, e to j, an integer times 2 pi, is also equal to 1. So, this complex exponential term is also equal to 1, because any integer multiple of 2 pi means you are on the real axis, and at which point the magnitude is always equal to 1 at the point 1, 0 in the complex number with real part 1 and imaginary part equal to 0. Therefore, the result of this integral is 0. Therefore, we have obtained a very important result. The set of harmonically related signals e to j k omega 0 t, k running from minus infinity to plus infinity, is an orthogonal set. Okay. Now we are ready to evaluate the coefficients of the Fourier series after all these discussions. Okay, we have x of t, an arbitrary periodic signal, and t0 is our fundamental period. X of t equal to ak e to jk omega 0 t is our Fourier series representation, k running from minus infinity to plus infinity. Now, how can we calculate the coefficients? For example, I want to calculate the coefficient a sub n. Now, suppose that we want to calculate a sub n for a particular value of n. For example, n equal to 10. The coefficient a sub 10. Okay. Now, similar to what we have done in Cn to find the coefficients in a certain representation given by orthogonal vectors, here we know that the complex exponential signals, the harmonically related complex exponential signals, form an orthogonal set. And therefore, if I take the inner product of both sides with e to j n omega 0 t, because I'm trying to evaluate the coefficient a n, I will be able to get rid of this series expansion expression containing infinitely many terms, and because of orthogonality, this expression containing infinitely many terms will reduce to a single term, or a result coming from only a single term. Okay, so we evaluate the inner product of both sides of this expression of the Fourier series by e to j n omega 0 t. Okay, so we have to now carry out these computations. Okay, let us now calculate the inner product of x of t with e to j n omega 0 t. And once more, without going into the details, we can claim that we are able to interchange the series expansion and inner product operations. K running from minus infinity to plus infinity, ak, the inner product of e to j k omega 0 t and e to j n omega 0 t. Okay, but from our previous discussions, we know that this term is equal to 0 for k different from n. As you see in this series expansion, k is our variable index and n is the index which is fixed. So k can take values from minus infinity to plus infinity, but for all values of k different from n, this inner product will give us 0. And therefore, this expression will be non-zero only when k is equal to n, and in that case ak will be equal to an, and we will have the inner product of e to j n omega 0 t inner product with itself. Now, what is this inner product? Let us look at that expression. E to j n omega 0 t inner product e to j n omega 0 t is equal to, from t0 to t0 plus capital T0, e to j n omega 0 t, e to j n omega 0 t, but with a conjugation. And as you see, this is e to minus j n omega 0 t. Therefore, the product of these two will be equal to 1, and therefore the result of the integral will be equal to t0. So an will be equal to t0 is the multiplier of an. Therefore, we can write this as 1 over t0, the inner product of x of t with e to j n omega 0 t. Okay? So we are able to calculate the Fourier series coefficient in a very straightforward way, by means of a very simple operation, by using the fact that the complex exponential, the harmonically related set of complex exponential signals form an orthogonal set. Now here n is a dummy index, so we can change it back to back to k. Okay, so ak is equal to 1 over t0. Now the inner product, let us write down the inner product from t0 to t0 plus capital T0 x of t e to jk omega 0 t, but now with a minus sign because of the conjugation coming from the definition of the inner product integrated with respect to t. So finally we have obtained the expression giving us the kth coefficient in the Fourier series representation of a periodic signal. Kth coefficient in the Fourier series representation. Okay, thanks a lot for watching.